All right, so 8:35. So yeah, let's get started. It's October the 4th. We are basically exactly on schedule. So after today, you will have, or should have, all the tools you need to complete assignment 2. And then next week, I guess exactly 1 week from today, we'll start on probability, which is where a lot of fun stuff happens, because you know, there's some cool proofs of things that are unexpected. But yeah, other than that, not much going on. Hopefully your assignments will be marked by the end of the week. No TA has mentioned that they're falling behind. So, but yeah, questions on the schedule or okay. So today we're going to look at Mergesort, and we're going to learn a new technique called unfolding. This is continuing our talk about recursion and recursive, in this case, recursive algorithms and how we analyze them by counting significant operations. Okay, so first of all, let's talk about what Mergesort is and what it does. Oh yeah, so this is counting significant operations, and we're going to analyze recursive algorithms and count steps using recurrences, which are simply recursive functions. So we know how to analyze a recursive function. We have a base case, we have a recursive case, and we have a guess at a closed form. That's what we're going to do today. When we analyze Mergesort, how we arrive at that guess is going to be a little bit different. Okay. So when we analyze Mergesort, our significant operation will be the number of times we copy an element to a new location. So Mergesort is not, well, it can be an in-place algorithm, I guess. Yeah, you can write Mergesort as an in-place algorithm. However, can you? I can't remember. But regardless, we're going to present a version that's easier to analyze. So where we copy things a bunch of times. And yeah, we're going to use a new technique called unfolding to find our closed form. Okay, so the idea behind Mergesort is the power of recursion, also divide and conquer. Right, so we don't know how to sort a list off the top of our heads. Conquer ER or OR? I mean, spell check has really ruined me. I don't know. Spell it however you like. Divide and conquer. So we don't know how to sort a list, but we know how to sort very, very small lists, right? So if I give you a list that looks like this, you can sort it. Basically, you just return it, right? It's already sorted. And if it has size 0, that's also the case. I can sort an empty list. They both come pre-sorted. So we have, if we're making a recursive algorithm for sorting, we have a base case. Our base case is a list of size 0 or size 1 that we can return perfectly sorted. So then we're going to develop an algorithm called Mergesort. We're going to sort a list of size n, where n is at least 2. And we're going to assume that if we make a recursive call on some value less than n, then that recursive call works, right? So that's, again, how we prove correctness of algorithms. Recursive algorithms is we show that it's correct in the base case, and then we make an inductive hypothesis. And that inductive hypothesis is that it's correct in the recursive case. And then we use those ideas to show that, well, we can sort a list, basically. All right, so for my Mergesort, my algorithm would go something like this. So if n, so item is my list, probably should be list. N is the size of this list. So if n is 1 or 0, then we return the item. It's already sorted. Otherwise, I'm going to divide this list into 2 lists. So I'm going to take half the elements, basically. You know, we're making some simplifying assumptions here that n is even, so we can divide it by 2. So I'm going to take half the list and copy it into a new list called left, and half the list and copy it into a new list called right. And then we're going to make a recursive call. So we're going to sort the left, and we're going to sort the right. These are recursive calls on lists half that size. So we're going to assume that they are correct by our inductive hypothesis. But now what do we do with these two sorted half lists? Well, so we have two sorted half lists. Maybe we can sort of merge them together, right? That's sort of, the title gives it away. So if we can take two sorted lists and merge them into one sorted list, then we can complete our merge sort algorithm. All right, so let's say this is a sorted list and this is another sorted list, and I want to turn these into a sorted list of size 8, right? So these have size 4 each, and I want to turn it into a sorted list of size 8. So what's my algorithm? So where do I start, I guess? What's the first thing I can do? So I'm going to copy all of these numbers from these two lists into this list, but I want them in sorted order. Yeah, for sure. I'm going to start at the beginning because I want, that's on the top. 2 is the smallest element in list 1. Let's give them numbers. And 1 is the smallest element in list 2. And so I know one of those is the smallest element overall, right? And in this case, 1 is the smallest element overall. So I'm going to copy 1 into the first location, right? And then 1 has been copied, so I'm going to update my pointer on list 2. At this point, 3 is the next smallest item in list 2. 2 is still the smallest item in list 1, and if I compare the two of them, well, 2 is smaller than 3, so I'm going to write 2 down next, and then I'm going to update this pointer. I compare 3 to 5. These are the two smallest elements I have left. Well, 3 is smaller, so I'll put 3 down next. I compare 4 to 5. 4 is smaller, so I'm going to put 4 down next. And I compare 5 to 6. 5 is smaller in this case, so I'm going to put 5. And then 6 is smaller than 8. Now I've run off the end of one list, so I can just basically copy the rest of list 1. Since I know 8 and 9 will already be in sorted order, and then I have merged two lists just by walking through basically each one in turn and making some comparisons. And whatever the smallest item I find, that's what I copy into the list next. All right, so this is, we call this a merge step. All right, questions so far? Okay. Yeah, all right, so I guess we already did all this, but if you like, the slides will remind you of the algorithm. So we end up with a final sorted list. And so we had two lists of size 4, and we want to count the number of times an element is copied to a new location, right? This is our stand-in sort of, again, this is, you can write an in-place algorithm, but you still got to copy things around. So, and memory access is sort of one of the slowest operations you're going to do on a computer. So it makes sense to count that. You also can count comparisons. So those are the two main ways you analyze sorting algorithms: is comparisons, count the number of comparisons, and count the number of memory accesses. But yeah, we'll stick to memory accesses for now. So we had two lists of size 4. We copied all of them into a list of size 8. So obviously in this case, we had 8 memory accesses. Or in other words, the size of list 1 and plus the size of list 2. Okay, so my algorithm merge in pseudocode would look something like this. Now this is a simplified version. If I have a list left and right, and then I'm going to iterate from I up to the size of the left-hand side plus the size of the right-hand side. And in every step of that iteration, I'm going to copy either an element from the left or an element from the right. So I will have the size of left plus the size of right. If we say N1 is the size of the left-hand list and N2 is the size of the right-hand list, that's how many copies we're going to make in our merge step. Okay. Okay, so now we have a complete idea for sorting, right? So we divide the problem in half until it's a manageable size, right? So our base case is size 0 or 1, and in that case, it's sorted. And then by my inductive hypothesis, every time I make a sublist that has size less than n, then I can assume that that gets sorted correctly as long as this merge step works correctly, which it does. We're not going to prove it, but we sort of saw an algorithm that works. So we can actually sort things. So we have a divide and conquer recursive approach. All right, so this is the algorithm. I'll go through an example of how it works sort of completely, and then we'll analyze it. Okay, so this is a unsorted list. Let's say we got this as input to our merge sort algorithm. The first thing we do, of course, is we divide it into two sublists and then recursively call merge sort on them. Okay, so, and then, at this point, I'm not changing the order of these elements. Just everything to the left is copied in the same order, and then everything to the right is copied to a list in the same order. These are still not, n equals 4 here. It's not 0 or 1, so I'm going to recursively make two calls again. First, I'm going to split them, and then I'm going to recursively make these calls. Right, so if I call merge sort here, then this is a call to merge sort on this smaller list. This is another call of merge sort to the smaller list. And these are merge sort calls. Sure, let's do the whole thing. Finally, I get down to lists of size 1, at which point I'm done. Right, so at this point, I take a look at the size of the list. It's size 1, so now I'm going to return from my call to merge sort. Okay, so we saw for a single recursive call how many, we copy everything from the original list, right? So on my call for merge sort here, if I look at the number of times I copy an element, it's the size of the input. And on this call to merge sort, it is also the size of the input. Of course, the input now is a size of half. And on this call to merge sort, the number of copies I make is also the size of the input. At the bottom here, these do not make any copies because they're size 1. But everywhere else makes copies. And so we could, sum up all the copies made here in the first step, plus everything in the second step, plus that one. But one thing we can notice is that, if we look at this recursion tree, on this level of my recursion tree, I make 8 copies. On the next level of my recursion tree as a whole, I make 4 copies here, and I make 4 copies over here, so that's 8 copies total. On my next level of the recursion tree, I make 2 copies here, plus 2 copies here, plus 2, plus 2. So I make 8 copies total. Here on this level, I make 0. But sort of, this is not really a proof, but it can help you to understand when you're trying to analyze something. We're assuming that they're even for now. At the end, we will look at what happens when they're not. It's really ugly, but it still works. Surprisingly ugly. So yeah, again, this is not a proof, but you can sort of inspect it and see that, well, every time I make a recursive call, if I look at all the recursive calls made at that level of recursion and sum them all up, then the number of copies is the size of the original list, right? So you can sort of get a sense of how many of these copy operations you're going to do overall. And in some sense, on this side, it's order n times the depth of the recursion tree, which, we will get to what the depth is in shortly, but if you divide everything in half each time, in fact, if you divide by any constant each time, then the recursion tree is going to be log, or the depth of the recursion tree is going to be log of whatever that, whatever you're dividing by. Okay. So yeah, n copies at level 1, n copies at level 2, n copies at level 3. No copies are made here, but that's fine. All right, so now we're on to the merge step, right? So we still don't have a sorted list, but we've divided everything down into its basic components. And now we have, in this case, 8 sorted sublists that we're going to merge together. So I made my original call was on, I called Mergesort on this list 7 and 4, and then I split them into 2 smaller lists, and then they return sorted, and then I do a merge step. And in the merge step, I simply combine these sorted lists. So here 7 and 4 become 4, 7. Here 1 and 6 becomes 1, 6. 5 and 2, of course, I compare, right? I'm using the merge algorithm. So I'm comparing the start of the list to the start of the list, start of list 1 to the start of list 2. Their list is only size 1 at this point, but it still works. Okay. Now that that step is gone, I had originally made a call on Mergesort on this list 7416. Now these 2 sublists are returned sorted. Now I'm going to merge them. So I use the old algorithm. I have a pointer to the start of each one. Well, 1 is less than 4. So I'm going to put that first. 4 is less than 6. So I will put that next. 6 is less than 7. So that goes next. And then I have a 7 left here. Okay. And then the same over here, right? 2 and 5 are both less than 8, and then 8 and 9. And then finally, I get my final merge step with my 2 sorted sublists. I merge them together and I get a final sorted result. Okay, so that's how Mergesort works. Questions? Okay, so we'll see a nice a demo of it later. Yeah, there's a fun little visualization program written by Robert Collier that I'll show you. That I wrote a new version of Mergesort for it using ChatGPT, and worked pretty well actually. So yeah. All right, but in terms of how many copies we made, so we saw how many copies we made when we go down the recursion tree. Now we're returning and we're running all the merge steps. So if we look at all the merge steps, well, of course, no copies are made here. That's where everything ends. There's no merge when I have a list of length 1. But when I have my 2 lists of length 1 returning, then I merge them. Well, I have 2 copies here, 2 copies here, 2 copies here, and 2 copies there for 8 total. And then this level, again, I'm going to make copies of each element, every single element once on that level of the recursion. So I'm going to make 8 copies, or n in general. And then to copy everything into my final list, again, I make n copies. So we kind of have a sense now of how many copies are made. During the course of this algorithm, we go down the recursion tree. So we'd have n times the depth of the recursion tree, and then we come back up the recursion tree, and then we have n times the depth of the recursion tree again. So it's going to be something 2n times the depth of the recursion tree. But we're going to formalize that. This just gives us an idea of what it should be. Why weren't there any copies at level 4? So at this level, we made a call to Mergesort on a list of size 1. That went down into my merge sort algorithm. It checked the length of it. It saw the length was size 1, so it simply returned. Right, so it didn't make any copies. It didn't split up the list, and it didn't merge the list because the list was size 1. So when I have these merge sort calls on a list of size 1, no copies are made. I just check the size and see that it was, yeah, okay. Other questions? Okay. All right, so let's take a look sort of formally at analyzing this algorithm. So here is my complete algorithm in pseudocode. Again, the merge, of course, I don't account for the fact that you're going to run off the end of these lists at some point, right? So that's sort of, this would not work if you tried to implement it exactly like this. But this is just to give us an idea of how it works. So yeah, let's analyze sort. And again, we're assuming that n is a power of 2, so it always divides evenly. So when I copy the left-hand side of the list into my left list, I have n over 2 copies. When I copy the right-hand side of the list into my right list, I have n over 2 copies. So I have, for any given call to sort, I have n copies total at that level. And then I have some number of copies being made recursively here, which we'll get to. But I just want to look at any given call, how much work is being done. So up here, I have n copies being made. So we have left to analyze the recursive calls. Well, these will just become a recursive, part of our recursive function. So now we have to analyze how many copies are made in this merge step. So in our merge step, of course, we have n over 2 here, plus n over 2 here. So our for loop loops a total of n times. And each time it loops, I either copy one from the left or I copy one from the right. Right, so I have n loops, and each loop makes a single copy. So my merge step is, of course, n copies total, where, n is the size of left plus the size of right. So, right, questions so far? Okay, so let's make a recurrence now for this. So we're going to let T of n be this recursive function. So T of n is the number of copy operations for a given call to merge sort. And I know that, well, when I split the array into 2, I make n copies. When I merge the 2 arrays of length n over 2, I make n copies. And then I have 2 recursive calls to sort here and here. And those are my recursive calls, so they're T of n over 2. Right, so now my complete recursive function is T of n equals T of n over 2 plus T of n over 2 plus 2n. Right, so this is recursive call number 1, recursive call number 2, and this is all the work I did outside of these recursive calls. Right, so this is the n over here and the n copies over here. Okay. All right, so now I have a recursive function, and I have a base case. My base case is 0. So yeah, I guess I didn't put that here, but of course, if my list is size 1, assuming again that n divides evenly, so we always get down to 1 and not 0. In this case, I make 0 copies. So yeah, I have my base case, recursive case. Now I want to find a closed form. I'm going to do that using unfolding. So the first thing I'm going to do is, of course, collect my 2 like terms together. And then I'm going to note that, well, T of n over 2, I can write it as T of n over 4 plus T of n over 4 plus 2 times n over 2, right? I'm just taking this n over 2 and I'm substituting it in everywhere that I see n. Okay, so then I have a recursive definition of t of n over 2, and I'm going to plug that in where I see that t of n over 2 in the original equation. Okay, so this value now is here, and then I can multiply this 2 times 2 here, and times this term here, and I get 2 times t of n over 4 plus 2n, right? This 2 cancels with this, plus 2n. Okay, and now I'm going to do the same thing again. I'm going to take t of n over 4. I note that t of n over 4 is equal to 2 times t of n over 8 plus 2 times n over 4. So I substitute that into here. And then I'm going to, do a little algebra. I'll multiply everything in the brackets by 2 times 2, which is 4, which means that, so I get 2 times 2 times 2 times t of n over 8. This 2 times 2 is equal to 4, which cancels this. So I'm left with 2n there. So now I have 3 of these 2n terms, and this is unfolding here. So at this point, I sort of spot a pattern, right? So every step I go down the recursion tree, I add another 2n, and I add another power to my power of 2 here and here. Right, so this is basically 8 is equal to 2 to the power 3, and 2 times 2 times 2 is equal to 2 to the power 3. So both of these are equal to 2 to the power 3. And at this point, I'm going to say, well, after k steps, I'm going to assume my algorithm ends. So my final closed form is 2 to the power k times t n over 2 to the power k plus 2n times k, right? So I have k of these terms here. Okay, questions? It's a lot of math there, but it's finding the pattern is the hard part, and then we verify by induction. So this is the pattern we've unfolded, and we assume that a recursion tree goes to a depth of k. So now the question is, well, how big is k? What is the value of k? Well, we know our recursion ends when we get down to a list of size 1. So whatever t n over 2 to the k is equal to, it should be equal to t to the 1, or t of 1. Okay? So what that means is that n over 2 to the power k is equal to 1, or n is equal to 2 to the power k. Okay, so we still haven't isolated for k, but at this point, we are going to, if we want to get back k, we can get k by taking the logarithm of base 2 of the right-hand side, and then also the left-hand side. Right, so if, I take log base 2 of 2 to the power k, well, the log base 2 of 2 to the power k is the number of times I can divide 2 to the power k by 2 until I get to 1, which is, of course, k. So yeah, I take the log of this side, and then I take the log base 2 of n, and that's simply the log base 2 of n. So I end up, once I take the log of both sides, I end up with k equals log base 2 of n. Okay, so the depth of my recursion tree is log base 2 of n. All right, questions? This is tough. We'll do an easier example after this, but okay. So now, right. So now, when n is equal to 2 to the power k, we get t of 1 here, and we get 2 of n k here, which is take the log of both sides. These are the steps we just did. So I have n times t to the 1 plus 2n times log base 2 of n, right? As mentioned earlier, in the base case, I do 0 copies. So t of 1 is equal to 0. So I can substitute that in there and I just get 0. So then my final guess at a closed form is 2n times log base 2 of n for merge sort. Okay, so that's a lot of steps. So what did we do? We counted how much work is done at each recursive call. That was my 2n, n here, and n here. And then I made a recursive function using my, t of n. I counted for these 2 recursive calls plus my 2n. And then I wanted to find a closed form, so I did some unfolding. I found a pattern. I figured out when the pattern ended, and then I used that to determine how many recursive calls were made. And then I could simplify and get a closed form. But still a guess. It's a pretty good guess, though. I mean, we took all the proper steps. We still have to prove by induction, but so questions? Yeah. K is the number. So every time K is the depth of the recursion tree, right? So K is, if you remember when we started with the list and we split it in 2, so K is the number of times we can split that list into 2 until we have a list of size 1. So it's not, so K has nothing to do, well, it is related to the size of the list, but it's really just how many recursive calls we can make until we hit the base case. Yeah, but those 2 things are accounted for here. Yeah. And then, yeah, so, yeah, hopefully that, all right, other questions? Okay. Yep. So this I got from looking at my algorithm. So what we saw was that here I made n copies, right? So I copied half of my list into the left, half into the right. And in total, there were n copies being made. And then in my merge step, well, I know that the left-hand side has size n over 2, and the right-hand side has size n over 2. And then I look at, well, then I have a for loop that goes from the size 0 to length of left over plus length of right, which is n over 2 plus n over 2 equals n. And each time I iterate this for loop, I either copy something from the left list or the right list. So I make 1 copy every iteration, so I make n copies total. So this n copies is the other part of this 2n. So it's just the 2n is all of the work I do on a call to merge sort outside of the recursive calls. Yeah. So if I did, if this algorithm was a little bit different and I did, I copied 5 things here for no reason, then I would add a 5. That's simply the work done outside of recursive calls. And then the recursive calls are this. All right, other questions? Yeah. Yep. So I assume that I assume that my recursion, I make k recursive calls. So and I mean, I know it ends somewhere. And I know where it ends is the base case. Right, so when does this return? If n is at most 1, and I'm making a simple assumption here that n will be equal to 1 at some point, because it's a power of 2. So I divide it in half each time, it's a power of 2. So at some point, I'm going to make a recursive call on a list of size 1. And that's where the recursion ends. Right, so I could write it as, let's say I took t of 8. equals 2 times t of 4, right? I make my two recursive calls, plus 2 times 8. Let's just call that 16. And then, well, this, I'm making a recursive call on a list of size 4, so I'm still going to be expanding that. So t of 8 equals 2 times t of 2 plus 16 plus 16. And then in the next recursive call, in the next level of my recursion, I have 2 times 2 times 2 times t of 1 plus 3 times 16. But at this point, my recursion is finished, right? I'm not making any more recursive calls. So my recursion ends when, well, I assumed that it ended at t of n over 2k based on my unfolding and the pattern that I saw there. And I know that it ends at t of 1, so it must be that these two things are equal. Right? Does that make sense? I'm dividing, each time I make a recursive call, I divide n by 2. And so it's n over 2, and then I divide that by 2, it's n over 4, and then I divide that by 2, it's n over 8. Which all of those are a power of 2, right? And then at the end, in this case, again, if I'm assuming I start with a list of size 8, then what I know is that 2 to the k is equal to 8, right? Because it has to be equal to n. So then I have t of n divided by n, or t of 1, and that's where it ends. Hopefully that's, I don't know. Sometimes you just got to let it sit, marinate for a while. Other questions that I can maybe partially answer? Okay. I'm trying to remember what I asked you to do on the assignment. This even, sometimes I forget to cover everything, so this might not even come up. I'm not sure. But you should know it. Okay, so I have a closed form, or I have a guess at a closed form, my 2n log base 2 of n, and I have, of course, my base case and my recursive case. So now I'm just going to prove the whole thing by induction, which means my base case, I want to show that t of 1 is equal to 2 times 1 times log base 2 of 1. Log base anything of 1 is 0, right? So the definition of log is how many times do I have to divide this by my base, in this case 2, until I get down to 1. In this case, I'm already at 1, so log base 2 of 1 is 0, which means this entire thing is 0. So my base case works. Incidentally, log base 2 of 0 is undefined for that reason, because you can't get to 1 from 0 by dividing it by something. So this is infinity or undefined. It approaches infinity the closer you get to 0. All right, so that's my base case. Now for my recursive case, or my inductive step, I'm going to assume that t of n over 2 is equal to 2 times n over 2 times log base 2 of n over 2. So I'm assuming this holds for some value less than n. All right, and I think I'd actually do this a little neater. Okay, so the base case holds. The inductive hypothesis is that this is true. So now I'm going to start with this and plug in my inductive hypothesis. So I'm substituting in for t of n over 2, this closed form. and then I'm going to do a little algebra, and hopefully everything will work out. I can see that this 2 and this 2 cancel. So I end up with 2 times n, and then times this log base 2 of n over 2. Log base 2 of a divided by b is equal to log base 2 of a minus log base 2 of b. Right, so that's a property of logarithms. If you multiply them together, if it was, if I did log base 2 a times b, that's equal to log base 2 of a plus log base 2 of b. So that's a property of logarithms, which means that I can take this logarithm and express it as log base 2 of n minus log base 2 of 2. Okay. So what's log base 2 of 2? Yeah. 1, yeah. So the log base, anything of itself, is the number of times I divide by 2 until I get 1. So that's equal to 1. So this is equal to 2n times log base 2 of n minus 1 plus 2n. I'm going to take this 2n, multiply it by both terms. So I get 2n log base 2 of n minus 2n plus 2n. And these, of course, cancel. And I'm left with the original guess. So I've proven it by induction that the Mergesort algorithm runs in 2n times log base 2 of n time. All right. Again, there's a lot of steps along the way, but the sort of the new step is the unfolding. All right, questions? Okay. I'm not going to do this. If you're interested, so assuming that n does not divide evenly by 2, then we would do something different. We would do an inequality here, because we're going to find an upper bound, but it's not going to be exact because we never know. There's a whole bunch of cases we would have to look at. So we're just going to do some rounding off. And yeah, if n is even, then of course we just have the same case as before. So we can make some simplifying assumptions that, well, we would say that it's less than n, floor of n over 2 is slightly greater than this, perhaps, or greater than or equal to, and the ceiling is less than or equal to this. Or sorry, I think I said that backwards. And you can do all of that. It's inexact, very detailed. If you're interested, look at this. I'm not going to go over it. It does have something to do with, so when you expand it out, the algebra is pretty simple, but then you end up with these 2 logarithms. And you can show that, what is it? I forget exactly how you show it, but it's something about the logarithm function and the fact that the slope is decreasing. Anyway. You can still show the same bound, but now it's going to be an inequality because it's hard to figure out every single possible case of a value of n and what could happen. All right, but yeah, so that's questions on that. Okay, let's do something a little more fun. Let's see what ChatGPT did for you. ChatGPT did some of it. Robert Collier wrote the original code for this in Java, and it's pretty cool. All I did in ChatGPT, I just did a new Mergesort that did things. Well, I'll show you the 2 algorithms and explain the difference. I believe this is set to Mergesort. All right, so Java cronk sorting demo, it basically sorts everything, and then it takes a picture and it divides it into I forget how, I think it's 32 by 32, and slices up the squares and shuffles them up. And then it shows you a visualization of different sorting algorithms. So this is merge sort. You can kind of see it's gone down to the leaves, and it's doing, you know, the merge operations on lists of size 1. When it gets to the bottom, it's going to go back to the top, and now it's going to merge lists of size 2. And then it's going to get to the bottom and go back to the top, and then it's going to merge lists of size 3, or sorry, size 4, etc. Yeah. They each have a, so we just give them a numerical value, right? So, yeah, right. Oh. So yeah, this is it's the Emperor's New Groove or something. I'm not super familiar. So yeah, all you do is you give them a number. You start in the top left, and that has number 0, and then this has number 31, and then this has number 32. So you know the order, and you just, yeah, you sort integers, and you use those integers to draw this thing, basically. Yeah. Other questions? Okay. So that was the ChatGPT version. That was pretty cool, because it starts at the leaves and does it level by level. It doesn't actually do merge sort. It does a merge sort that's suited for visualization. I can show you the original merge sort. Merge sorter 2. Still remember some Java. Yeah, it's doing the same thing. It's sorting. So now it's going to actually, instead of doing it level by level, it's going to go down into one subtree, and it's going to do all of those things at once. So you can see once it finishes, you know, it goes and does all the ones of size 1, and then it merges them, and then does all the ones of size 2. So it's doing it. If you look at the recursion tree, I guess I have no chalk. Yeah, so it's going to do like the left-hand side, and then as it finishes part of the tree, it's going to, you know, complete that part, and then it's going to go down into the next branch, and then it's going to complete that. So this is the same algorithm. It's just this is the actual order that it gets evaluated in, right? So this is closer to what your computer does, where the other one is just starts at the leaves and works its way back up. Yeah, but then when you get to the bottom, of course, everything sort of happens really quickly. Boom. All right. Just for fun, since we're here, are you guys familiar with selection sort and bubble sort? Yeah. Right. Professor who? Sorry? Farah. Oh, yeah. Yeah.
He's taught me a lot about Mergesort here.
Cool. So this is just, there's nothing to do with our class per se. This is selection sort, though. It runs a little bit slower, but it's basically, I go through the list, I find the smallest element, I put it in the first location, go through the list, find the smallest element, put it in the next location. So this actually runs in n squared time, so it's a little bit slower, but you can see how it, you know, sort of builds the list in a linear fashion almost. So yeah, every time it goes through, it finds the smallest element yet to be found and puts it in its correct location. So then you get this very long version of Cronk. All right. Okay, and then in addition to that, that is really slow. Okay, I think we get the picture. Bubble sort, and then I'll show you quick sort. Quick sort is not as nice a visualization as the merge sort, but you still kind of get an idea. So bubble sort of does the opposite of selection sort. It goes through, it walks through the entire list, and anytime it finds two things out of order, it switches them. And the effect of that is basically the larger items get bubbled up to the top, and then everything else sort of moves along with it. And then eventually, again, this is an n squared algorithm, similar to selection sort. There's a lot more movement in this one, though. It is super slow. Okay, so I think we get the idea. And then I'll just show you, so, oops, that was just for reference, but quick sort is something we do actually see in this class. Oh, come on. Oh, all right, well, let's go with the original quick sorter. I mean, it was just working up in my office. I forget that I must have accidentally introduced a bug somewhere. Oh, is that what I did? Yeah, you're right, eh?
Wrong.
Yeah, no, I did accidentally, yes. Thank you, yeah. All right, let's see quick sorter. Okay, so this, yeah, I have a couple different versions of quick sort that sort of visualize things slightly different, but the algorithm's still the same. So yeah, you saw in the first step how everything, so quick sort, if you recall, picks a pivot and then puts everything less than that pivot to the left, everything greater than that pivot to the right. So every once in a while, you see a big jump of things. But in general, of course, it's doing the same thing the second version of Mergesort did. It's evaluating it in the way that your computer would. It goes down to the bottom of this subtree first and completes that and comes back, finishes the next subtree. So yeah, that's quick sort. Cool. Yeah, so somebody asked, how is that implemented? How does this work? So it just takes, so Java, you can take an image and you can slice it up into other images. And then again, it just associates an integer to each of these little squares, right? So I have, I know the original image, and each of them is associated with a number, and then I just shuffle those numbers. So then when this is drawn to the screen, it's drawn based on an array list of integers. And it says, okay, so the first integer might be 560. So it puts the 560th square in the top left-hand corner, and then it keeps going like that. So then as you sort it, you get these other array lists that are closer to being sorted, and then you can kind of see exactly where each element is. Yeah. All right, other questions? Okay, what to do next? Okay, do binary search, but I think I'm going to do something. So there is a binary search that does something very similar, although simpler to the analysis we did in Mergesort. So it's a nice, if we have time, I'll come back to it. But again, it's used as unfolding to find the pattern. The pattern is much simpler in this case. But I do want to actually do this question because this relates to your assignment, right? So there's a part on your assignment. I do give you the, so there's basically a summation and There's a closed form. I give you the closed form, but I just want to show you how it works. So I have this algorithm called Thanksgiving, and I'm going to count the number of times eat a bite runs and also the number of Newton's IPA that I drink. So if I visualize this as a recursion tree, then yeah, so n equals 1. I drink a Newton's IPA and I return. So my base case is n is equal to 1. Otherwise, I make a single recursive call to Thanksgiving on a list, or sorry, on a value a third of the size. And I'm going to assume that n is a power of 3. Okay. So how many Newton's IPA do we drink in this algorithm? 1, yeah. So if you look at the recursion tree, I only make one recursive call. So I start with a size n, and then I make a recursive call and I have size n over 3, and then I make a recursive call, I have size n over 3 squared, until I get down to 1, and that's my base case. So in Mergesort, our recursion tree branched into 2 branches at every step, but in this case, we only make one recursive call. So I drank a Newton's IPA in my base case, which you could think of as the leaves of your recursion tree. So here I drink a single IPA. Does that make sense? Questions? Okay. So yeah, let's look at how many bites of Thanksgiving dinner we eat. Okay, so I'm going to, let's develop a recurrence. So my T of n will be the number of times my eat a bite function is run. And then I'm just going to write this as a recurrence based on inspecting the algorithm, right? So I want 2 terms here. I want all of the work that's done at a level of a recursive call plus the size of plus the recursive call. Okay, so T of n, well, assuming that n is greater than 1, right? So if n is equal to 1, or sorry, let's do the base case first, actually. So T of 1 is equal to the number of times I run eat a bite. In this case, that's 0, right? So T of 1, I drink a beer, and then I'm done. Okay. So now for n that's greater than 1, I want an expression for T of n. In that case, I look at what happens at that level. I run a for loop. For loop runs n times, and I eat a bite n times, and then I have this recursive call to Thanksgiving on size n over 3. So we'll start with the recursive call. And then here I have, so T of n over 3 is the number of times eat a bite is run by this call to Thanksgiving of n over 3, and then plus n is my for loop. So I run the for loop n times, I eat n bites of turkey. All right, so I have a very simple recursive formula in this case, but we're going to expand it and find the pattern and then prove it using induction. Questions so far? Yeah. I just chose a function. It's a recursive function, that's all. I could have called it, in this case, it's T for Thanksgiving, but yeah, so you might see C or B or whatever, it doesn't matter. Yeah. Other questions? Okay. So let's expand this a little bit. Well, I know T of n over 3 is equal to T of n over, well, n over 3 divided by 3 is n over 3 squared plus n over 3, right? I'm simply plugging n over 3 in everywhere I see n in my original equation. So I can rewrite this as T of n over 3 squared plus n over 3 plus n. And then, of course, my T of n over 3 squared is equal to T of n over 3 cubed plus n over 3 squared. Again, I'm just substituting n over 3 squared for everywhere I saw n in the original equation. So I expand this out more and I get T of n over 3 cubed plus n over 3 squared plus n over 3 plus n. All right, so I kind of see the pattern emerging here, right? So I can probably write the next step just through inspection. N over 3 to the 4th plus n over 3 cubed plus n over 3 squared plus n over 3 plus n. And so on until I get to the base case. Okay, wow. All right. So my base case is T of 1. So again, I'm assuming I go down k levels. T of n over 3 to the k plus n over 3 to the k minus 1. So if I look, this is 3 to the 3rd and this is 3 to the 4th, and it's always the latest one is 1 less than the denominator in my recurrence. So then this is plus n over 3 to the k minus 2 plus n over 3 plus n. All right. Everybody still with me? Yeah. Because I'm substituting in, yeah. So in the first case, I have T of n equals T of n over 3 plus n. Right. So now my T of n over, so this is, my original call. The next call I make is to T of n over 3. Well, at T of n over 3, I eat n over 3 bytes, right? So if this is n over 3, then my loop is n over 3, and I eat n over 3 bytes. So I put that there. So yeah, in the original call, I ate n bytes. In the first call, the first recursive call, I eat n over 3 bytes. In the second recursive call, I eat n over 3 squared bytes, and so on and so forth. So in the one sense, I can get there purely by unfolding, but if that doesn't make sense, you can go back to the algorithm and think, well, what exactly happens? Right, well, I eat n bytes, and then I make a recursive call at n over 3, so then I make n over 3 bytes. Then I make a recursive call at n over 3 squared, so I have n over 3 squared bytes, etc., until the recursion ends. Other questions? Okay. Okay, so I have a pattern. This part's going to be pretty ugly. Again, I know my recursion ends after k steps. I also know my recursion ends when at T of 1. Right, so that means n over 3k right? That was the last call that I made. And in this case, n over 3k is equal to 1, which means that n is equal to 3 to the power k. K, again, is the number of recursive calls that I made. So I'm going to take log base 3 of both sides. Log base 3 of n, and then log base 3 of 3 to the k is simply k. Okay, so k is log base 3 of n, and that's the number of recursive calls I made. Yeah. Okay, so that means if I back up a little bit here, so this is equal to T of 1 plus n, and then 1 over 3 to the k minus 1 plus 1 over 3 to the k minus 2 plus n over 3 plus n. And again, these are all the bytes of turkey I've taken, right? So n here in my next recursive call, I took n over 3 bytes. In the following recursive call, I took n over 3 squared bytes. In my last recursive call, I took 1 over 3 to the k minus 1, and we're going to evaluate what exactly that is. This is equal to 0. So this is n 1 over 3 to the k minus 1, 1 over 3 to the k minus 2. Whoops, this should be 1 and 1. Because I took the n out as the common factor. So this is equal to n I equals, what is it? 0 to the k minus 1 of 1 over 3 to the I. Okay, so now the question is, I have an expression, I just need to find the closed form, and I have this summation. And I think I give you on your assignment this expression. So S of n equals I equals 0 to k minus 1 of 1 over, what did I do here? All right, let me write it out. S of n equals a times r0 plus a times r1 plus a times r2 up to a times r to the k minus 1. And so this is an expression where this is sort of an expansion of, a representation of this summation, right? So it's a geometric series. And in this geometric series, A is my starting value and R is the common ratio. Okay, so every time I add a new term, I multiply times 1/3, and I get this, which I can, in this case, if I plug in R equals 1/3 and A equals 1, I get this summation, okay? And there's a closed form for this summation, which I'm going to teach you not today, but somewhere in a couple lectures. I'll show you the closed form, but I'll teach you how to derive it in a couple lectures. And it is this. Okay, so I give you that closed form on your assignment, and you at some point are going to end up with something that looks like this, and you're going to apply this closed form. Okay, so what does this give us? Well, if I plug A equals 1 and R equals 1/3, then I get, well, this would actually be, of course, S of n equals 1 minus R to the log base 3 of n, 1/3 over 1 minus 1/3. All right, so it's a bit ugly, but that's if I plug 1/3 in for R, log base 3 of n in for k, and 1 in for a, then I get this expression, which I can then simplify. 1 minus 1 over 3 log base 3 of n. Right, so 1 raised to any power is simply 1. So I'm going to take this exponent and just apply it to the denominator here. 1 minus 3/2 is, 1 minus 1/3 is 2/3. 3 to the log base 3 of n is n over 2/3. And then you can fiddle around with that a little bit, and you get, I believe, 3/2 times n minus 1. Okay. So again, you're going to see something similar to this on your assignment. You're going to be expanding it out using unfolding, and you'll get something that looks like this. I gave you, or I pointed you at this closed form for a geometric series. So you're simply going to plug in the values you get for K, A, and R into this closed form, do a little logarithm magic, right? So K is probably going to be a log, maybe, actually, I don't remember, might be a log. Whatever it is, won't be too complicated. And then I get 3/2 n minus 1. Yeah. Yeah. And then all of that times, what's that? Yeah, you're right. Yeah, sorry. I got ahead of myself. You're right. Yeah. Yes. So this, yeah. So this expression evaluates to 3/2 n minus 1 over n. And then when I go back to this expression, then I get n times 3/2 n minus 1 over n. And then these n's will cancel out, and you're left with 3/2 n minus 1. Yeah, thank you. Yes. All right. Hopefully some of that makes sense. Yeah. What's that? Sorry. So I just have this expression. So I could have actually plugged n in for a if I wanted. That would also make sense. But I have a geometric series, and if I generalize a geometric series, then I have my starting term, which is, in this case, 1, or it could have been n. And I have my common ratio, 1/3. So r to the 0 is 1/3 to the 0 is 1. So this expands to, 1 plus r raised to the 1 is 1/3 times a is 1 plus 1/3 squared. So r squared, 1/3 squared is. What's that? Sorry. In the previous question, well, in the Mergesort. Yeah, yes, this I wrote in the, this is in the reverse order of the way they would actually occur. Yes. Yeah.
A is between 0 and 1, right? For geometric series.
Yes. Well, no, a can be any value.
It can be any given number.
Yes, it's just the starting term, right? And
Yeah, but R is common ratio.
R is a common ratio. R does not have to be a fraction. R can be, it'll still work if R is like 2 or something like that. Yeah. Okay. Cool. Yeah, I'll clean this up and I'll post it on your on Brightspace. Yeah, this happens when I get away from the slides. I draw things over here and there and everywhere. McKeel is nice and organized, but I'm still learning, I guess. All right. Any other questions? All right, we got 5 minutes left. Uh, 5 minutes maybe. It's not quite enough to do. You know what, I'll show you, we'll just look at binary search, and then next class, we'll quickly solve it before. Okay, so binary search algorithm, I'll explain it in the next 5 minutes, and then next class we'll do the analysis. But basically I have a sorted list. Right, so, and I have a bunch of elements that are maybe in alphabetical order, so B, D, F, G. And then I want to search for something. And instead of starting at the beginning and just looking at every single element, because it's in sorted order, I can take advantage of that. So what I'm going to do is I'm going to start by checking the middle of the list first. And then if that's the item we're looking for, of course, we're finished. But if it's not the item we're looking for, then because it's in sorted order, I know if it's going to be to the right or to the left of this current item. Right, so if the item I'm looking for is, or sorry, if the item I found is greater than what I'm looking for, then I'm going to search in the smaller half. And if the item I found is smaller than what I'm looking for, then I'm going to search in the larger half. Okay, so for example, I have a sorted list and I want to verify that 17 is either in the list or not in the list. And the first thing I'm going to do is I'm going to jump right in the middle and say, is this 17? And of course, the answer is no. But of course, I know this is not 17, but I know something more. I know that 17 is greater than 14, which means that I can search now just this part of the list, which is at most half of the list. And this part I can completely ignore. So I've cut my problem size into half, at least. At this point, I'm again going to jump into the middle of the list that I have left, right? Give or take 1. I'm going to say, is 2217 equal to 17? And the answer is no, but I know that 17 is less than 22. So now I'm going to reserve my search for these 3 elements, and I'm going to ignore the rest of the other half of that sublist. I'm going to jump into the middle again and say, is this equal to 17? The answer in this case happens to be yes. And so I'm done. I looked at 3 different indexes. I just jumped around and I found the thing that I was looking for. Whereas if I did a linear search, then I would have made 9 comparisons before I found the element I was looking for. So this is an example of a binary search, and we're cutting our problem size in half each time. And yeah, we're going to get a similar answer to, well, not quite the same, but yeah. Okay, questions on that? All right, so next class we'll do a quick analysis using unfolding. It's a lot easier than merge sort, and hopefully it'll illuminate some of those things. I guess that's in a week, actually. Yeah. Yeah. Yes, we're done. Yeah.
We transform it now.